Hello guys, Sir Libby again. We will be moving on to compression members, uh, and we all know that the basic example of a compression member is a column, although we can regard other secondary members uh, to behave as compression members also. In our course of discussing compression members, we will be focusing more to columns, since columns are one of the major component of the building. So when we deal with the tension last time, we more or less saw the importance of the connection uh, in considering loads for us to be able to ensure that the a member will behave as such. The connections are the plays a major role in the design. So when we talk of compression, it is not to say that the connections are not significant, but compression tells us more to be cautious in terms of instability issues. Okay, because a compression member tends to stabilize the behavior of a component or a series of components. The issue here does not only lie on connections, but also lies on how stable your compression member is. And instability is actually a question of when and how buckling may occur. So when we're talking of buckling, we are actually considering instability as a failure in that regard. And the two types of buckling we can deal with maybe global or local. So when you say global instability, you are referring to the whole structure or the whole component. And when we talk of local, we are referring to a, a part of the structure or a member. Okay, so with this, we can say that tension and compression is regarded in a different manner. It is addressed in a different manner. So we have to understand separately the concepts, the issues, the guidelines involved in the analysis and design of compression members. So for the uh, terms and vocabularies in terms of the notations, we will be using the following. Okay, So the first, of course, are stresses, critical and residual. The third one is actually a frame slenderness parameter. So when we talk of G and G prime, we will be talking of the frame as a whole and not the member, not just the member itself. So I, it has something to do with the property of the member. Okay, so L, and L are considering the length in terms of the effective and the nominal length. So for P and NPU, these are now the capacity and required loads or factored loads carried by the compression member. Of course, we have to add here the value of P for columns to give us the design capacity. R is also a property of the member. T, TW, and TF also a property in terms of dimension. And lambda C, lambda R, and lambda P are also properties that we compute to determine the limiting. Okay, so it has something to do with the limitations on the width to the thickness. Okay, limit. Okay, so again, this has something to do with local stability or local buckling. Local and of course also global, because we have here the lambda C factor. Okay, for some mathematical whereabouts of how columns column equations are considered, so we have here a simple example of a buckling problem, a column buckling problem, the proponent of which, of course, is very famous, no, in the name of Euler. Okay, so the elastic buckling load, which was introduced by Euler, is derived by means of the differential equation of this elastic curve of a beam. So if we consider this elastic curvature as our basis for the differential equation, we can write down this particular differential equation of the elastic curve of such a beam. This time the beam and the column are just the same in terms of the flexural behavior. Of course, the only difference is your moment is not measured in terms of transverse load, but it is measured in terms of the compressive load. So M here has something to do with the moment that will cause this to buckle. So this is simply equivalent to P y, or negative Py. So there's a correction here that your bending moment is a negative, okay, bending moment. Okay, so if we look into this free body diagram here, okay, so your bending moment is actually the uh, oppositely directed with that of the Py here. And since this is counterclockwise, so this has a negative sign, should have a negative sign. If we consider the sign convention in terms of the direction of the moment. Hence, fourth, if we continue to derive now the differential equation of motion, or sorry, the differential equation of the elastic curve, so your differential equation will be this one. So I just want to rewrite it here. It's y prime plus p over ei y equals 0. Okay, so this is an ordinary differential equation. It's not very difficult to take the solution of this. And the common way of deriving a solution on such differential equations by the method of characteristic roots, for which the general solution may be derived simply by getting the roots of this characteristic equation. So this is your auxiliary equation, or the characteristic equation there. Okay, so the m here is a variable, an operator which defines the degree. So this is the degree of differentiation we have. Okay, so this is a second degree. So this is m squared, and this is a 0 degree. There's no a derivative here, so this is m to the 0. So your equation now will reduce simply to this one, and if we take the root of m, so this is simply equivalent to plus or minus the square root of p. This is plus, of course, p p all over ei multiplied by an imaginary number, because this is negative. Okay, so if we take m here, this is actually the square root of negative p over I. So in order for us to get the square root of a negative number is equal to the square root of the number multiplied by I squared. Okay, so the square term here is only up to this point. Okay, so this is equivalent to plus or minus, so this is a negative 1, so the square root of negative 1 is I squared, so this becomes now I multiplied by p over ei. Or we can simply write it like this. It's just the same. So for the solution of such, when your root are unique, okay, or distinct, they are distinct and repeated. Sorry, they are not repeated because they are distinct. Okay, so this is now different plus and a different value in the minus. So when the root is an imaginary number, your solution will be in the form, simply in the form y is ae to the mx, okay, plus be to the imx. There's an I here, okay. So the I there, okay, the I there actually is the imaginary number. And since we note that EIX is equal to cosine x plus I sine x, by way of having what's this? This is an exponential identity. Okay, this is an identity that relates the exponential number e to your trigonometric cosine and sine. So the proof of such may be derived by simply taking note that x is an angle assumed to be pi, if this is x is equal to pi, then ei to the pi is simply equal to cosine of pi plus I sine of pi. But since I is multiplied by 0 here, the sine of pi is 0 and the cosine of pi is negative 1, we have now reduced this identity into a simpler identity that can be uh, very well uh, proven by substituting the value of e. So if I raise 2.718 I to the pi, this must yield to negative 1. Okay, so e is an exponential number, which is also called the Euler number. Okay, so we can make use of that. So this is, by the way, there's a correction here I'd like to make. We can remove the I there simply because the I is already a part of. Okay, so this is simply m. Okay, mx and uh, minus. Okay, so this is m, this one plus, and the other one is m minus. Okay, or we can call it, sorry, we can call it by m1. We just call it to avoid confusion. Let's be more mathematical, no? So this is e to the m1. Okay, m1 x, and this is e to the m2 x, where m1 is square root of p over ei x, and m2 is negative square root of p over ei x. So this is mathematics. So you just take note of what you learned in math. Okay, to continue applying the boundary condition or simply substituting the value of those equations by substituting x equals 0 and x equals L. So in which y at that point is 0. No? So what is y? Y is the deflection. So this is a boundary that gives you a value of y which is 0, because if this is the curve, okay, at this boundary, okay, so this is your x-axis, this is your y-axis. So at this boundaries here, at x equals 0 and L, your value of y here are both 0. So we simply say 0 is equal to a cosine of 0, 0. So you substitute the value of 0 here and 0 here. Okay, you get a cosine of 0 is 1, b sine of 0 is 0. So a is equal to 0. And then you substitute here L. At L, this is square root of p over EIL, square root of p over EIL. Okay, so what is your value of A? A is 0, so this whole here becomes 0. And b sine square root of p over EIL is called an eigenvalue equation. And this eigenvalue equation now will give us a value of b not equal to 0, and this must be equal to 0. So this is just a logic that b cannot be 0, because if b is equal to 0, then you have a trivial solution. So to have a non-trivial solution that must exist, b cannot be 0, therefore your sign square root of p over EIL is equal to 0. And here comes now the the values of different values of angle that will create or give a result of 0. Okay, so sine of an angle is equal to 0. So the angles now are multiples of pi, which means that if I take this angle, okay, so this is my angle n pi. Okay, so this is simply the arc sine of the square root of or arc sine of 0. Okay, so this is a sine of the angle is 0. So the arc sine of 0 is square root of p all over EIL, which is n pi. And if we equate n pi and this is the angle. Okay, so this is now the angle which is equated to this. We can say that this is now a multiple of pi, which is starts from 0, 1, 2, 3. Okay, so your angles now becomes 0 pi, 2 pi, 3 pi, etc. Okay, so all the sine of these angles are 0, such that your p now, by making use of this equation, becomes n pi squared over L, or n pi over L squared multiplied by EI. And if we choose a critical value, meaning to say we choose the least, okay, the critical value is the least or the smallest value that the column can carry, will give you an n equals 1. So this is now 1 times pi squared over L squared times EI becomes your Euler elastic buckling load, which can also be written in terms of PE. Okay, so the letter E here stands for Euler elastic, and the CR there stands for critical. So in terms of stress, if we divide this by A, we take note that the force divided by the area is simply a stress. Okay, and if I divide this both by A on the other side, okay, AGL squared, take note that I over A is equal to the radius of gyration squared. Okay, so note that R squared is equal to I over A. Okay, so I over AG becomes now what? R squared. So this becomes pi squared E R squared all over L squared. Or simply, you can make use of this equation as your Euler elastic buckling stress. Okay, later on we will be introducing a K value there in order to capture the effective length as your uh, property of concern. So the above equation is the basis for the column strength that we are be deriving on the next video. Okay, so let me stop at this point and entertain your queries if and concerns if you have some. Thank you very much.